Okay, so we're going to go over an exercise in the crafting of machine learning systems book that I'm developing, and afterwards I'll put the link to the draft in the blog so everyone can have a look at the section. The section talks about, in general, talks about the scientific method and how it maps to machine learning development. And specifically, this section talks about conjecture. And it outlines that the main conjecture in a machine learning system is that the data we have will enable generalization, which means that on new data it will perform as expected with respect to some business requirement. And in order to better understand this, there's several elements that are identified to be things you have to be on the lookout for a good solution, machine learning solution. One is that you can quantify the business requirements, so we'll know if we have a generalization. So if we say that 10% of the chatbot calls are going to be diverted to a human agent, that's something we can quantify. So that could be something we want to measure and see that it generalize. We have some ideas of what are the factors that are impacting and whether the system is behaving or not. Otherwise, we can't design an experiment. Well, there's a lot of discussion about that in the book that we won't go into now. And typically, we need to identify what we call a model. So a model is a space of possible solutions that we search in for a good solution. That's a model. Okay. And the exercise, and one of the things that I'm saying here, that you need to be aware of the model you're choosing, even if it's explicit. So sometimes it's implicit, sometimes it's explicit. Many times for people it's implicit because they just pick up some library that does some sort of learning in Python, say. So they don't understand what are the model that they are choosing, and they don't understand what are the degree of freedoms that are associated with the model. And the objective of the exercise here is to show you how important is the choice of a model, basically. So this is the exercise, and Guy will take us through the exercise. So Guy, the floor is yours.
Thank you. I'm taking the share screen. Okay, can you see my screen?
Yes, we can see your screen.
Great. So specifically, we're handling this exercise from the book. I'll start with defining the problem. We have a parabola that we wish to learn, which is a second-degree equation with three parameters, A, B, and C, of which we want to learn. We're also given a data set, D, which is the X and the value of the function at these points. And we want to use linear regression model to form another function which tries to learn f of x. The function is g of x, and it's a linear equation with just 2 degrees of freedom. d times x plus e, which are two degrees of freedom. So
just 2 points here. Okay, guy. So one point is that when we do the learning, we don't know the parabola. And we're telling you now that we're trying to learn a parabola, but in fact, think about it as if we don't know that the relation is a parabola. That's one thing. And maybe we have a hint, but we don't know whether it's a parabola or we have some information on the domain, but we don't know for certain that it's a parabola necessarily.
yes,
That's one thing. The other thing is that when we say a model, technically, when you say all of the linear line, 2 parameters, that's a model. So that's the search space. One of the search space guy is going to be talking about. So when you say a model, it's all of the things you're going to pick up your machine learning solution from, and that's your search space. So a model is a search space. In this case, one of the models is the linear model. So you have 2 parameters, and the relation is a linear relation. Okay. So back to you. Back to you.
Okay, thank you, Eitan. Okay, so I'll start with simply defining f of x in the Colab. You can see it defined as so: f of a times x squared plus b of x plus c, and which I randomly assign values, which is a equal 1, b equal -2, and c equal -3. We evaluate between -5 and 5. This is the function. And when we plot it, you see this behavior, which matches this function. Okay, so let's continue. And next, we generate the inputs and the outputs. This is x, and these are the points. The x is just from a set of points starting 100 points from -5 to 5. And y is the result of f of x. We simply apply f on each point in x, and we try to create this function, g of x. Which
Another comment here. So this is the data point. So in reality, this is the only thing you get. So all you have is the 100. How many points here?
In this case, 100.
Yeah. So you only have the 100 points, right? You don't know that the relation is a parabola, and you have 100 points.
Exactly. And we're trying to create this function, g of x, which it has 2 parameters, d and e. And let's start with the question: do we expect the results to be good? Well, we already know f of x is not linear. It's a power of 2, and g of x is linear. So we don't expect the results to be good, as they are from different degrees. But we are going to try, and we're going to see where it fails.
Right. And you see, the interesting thing is that it's highlighted here in a very simple setting on purpose. So basically, you make a choice on your search space. Now, in fact, the first choice that is a silly choice, right? We don't expect it to do anything good, basically, because but in reality, you do that all the time. You make very silly choices about the technique you're using for learning. You have to infuse domain knowledge and understanding in order to make a good choice, actually. So that's one of the messages here.
In this example, it's very easy to see that f of x is from a different degree of g of x. But if we're going on very high dimensions like images and audio, sometimes this question is not so trivial. And as Eitan said, call it silly. It's silly because we know the answer, of course. If we work in high dimension, this from a silly problem becomes an extremely hard thing to notice.
Yeah. Okay. And what we want to see here is that actually your choice really impacts whether you can learn or not. So that's what we're going to see.
Okay. but don't spoil ahead. So
Yeah.
let me just show it first.
Yeah.
Okay, so we've tried to learn it, and we come with this according to NumPy polyfit, one dimensional. This is the model I chose, which is simply a linear regression. I got these parameters -2 of something and 6. And we checked using the MSE error, and we got quite a big of an error, 64. So let's look at it. If we visualize g of x, it's a linear function, as we defined it to be a linear function. And when we overlap it on f of x, you can see that f is not, and which explains why the huge mean square error. You can also intuitively see why the algorithm, air quote, chose g of x, because it's kind of in the middle. So in the ranges we randomized for generating f, this is as close as it gets, but you can also see that it's not a fit. It's a bad fit, but it's the best thing we can produce under this limitation. So are there any pair that will work? Well, probably not. Not probably, there isn't, because this is a line and this isn't. We can optimize the mean square error or any other error function, but it will never be perfect because they are different shapes or has different polynomial degree. So what can we do? The assumption is that we only have linear regression. Linear regression does not work on higher dimensions, but we can add different parameters, and we can use this trick by simply adding a specific parameter, not any. If I wanted to write down the equation of g of x when it's different, you'll get something like this: x1 plus b of x2 plus c. This is still linear. We have two parameters here, x1 and x2. And if we just place x1 to be equal to x2 square, we get a higher degree of a polynomial. This is the trick we're doing. This is, in fact, still a linear because we're trying to evaluate A, B, and C. The linear regression does not know we did this trick. For all it's concerned, it's a different parameter. It's our job as a data scientist to do this kernel, this trick. So let's see how it goes. So this is our new function, g of x, which is actual g of x and x squared. And we place parameter 1 times x squared plus parameter 2 of x plus c, the third parameter. And notice I only need 5 points, the size of the data set. I can change it, but to learn a parabola, you just need 3 points. So we'll use a lower number, but it's really not that important. So I generate our data sample. We start by creating the points going from 5 points from -5 till 5. This is our x, the starting x. We started using it directly, and then we're squaring it. So in fact, our input is x and x squared. You can see here, I just squared this entire vector. I use a linear regression again, and now it gives the first parameter for here, a, the second parameter, and the third parameter. And now we get mean square error of 0, which means we are on exact fit. So the function it evaluated is exactly the parameter we chose for f of x. It makes sense. It chose correctly the exact numbers. Therefore, the mean square error is 0, and g of x is exactly f of x. And when we overlap it, you can see it's exactly the same. You only see 1, but there are 2. Because we don't need to directly evaluate the parabola. This is the idea of linear regression. We just need to evaluate these parameters and not the parabola. You don't need more than linear regression to solve higher dimension using this trick. And you can also go higher with, again, x times 3 and 4 and 5 and so on. Just consider it for a linear regression of multiple parameters. These, and these. And again, it's linear because of this sign. These are linear to each other, and the points simply match this. but it's still a linear regression. So let's look at the question here. No, it does not. And can you implement it using, instead of using x squared? I mean, you said, did the result improve? Yes, they improved. They became the optimum. They are perfect now. Can you explain? I think we just did. And that's it.
Yeah.
This is how you use linear regression to evaluate higher degrees polynomial or higher degrees dimensions.
And you also see that by changing the choice of a model, you can either learn or not learn. So the model you choose is very important for learning, and you need to choose a model that fits the task. And we talk a lot in the book draft. We talk a lot about how to do this. So Guy, thank you for this.
For listening.
Yeah. And any questions?
Not for me.
Someone you
Yeah.
have a question.
Yeah. Yeah. So I was asking that the linear equation which we are targeting basically to get the function, and if we like if the x becomes a very large number or very small number, and as you were mentioning that we are trying to come to a convergent point. So if it happens that, my question is that if it happens that the due to the misleading x, instead of converging it becomes divergent. For example, like I want to come to a point where my optimized point, like what I understood, might be my understanding incorrect, somewhere I joined late little, but my question is that if the x which I am putting, like from it is from -5 to 5 within that point, right? So if the x which like the for this linear equation, if the x I am putting I'm checking the previous result, and based upon that I am taking the direction, like whether it will be a negative direction or whether it will be a positive direction. Accordingly I am increasing or decreasing the x value. So if instead of becoming convergent, which is my wish that I want to converge this equation, if it becomes divergent, it going towards the wrong path, then what shall we do? Shall we put any optimization? Yeah, yeah. So I want to reach that uh, that uh, that top bottom. For example, yeah, there I am right now, or wherever I want to reach the bottom, but uh, uh, yeah, but instead of going bottom, I am going upwards. So how shall I detect that? And if that is happening, so how shall we optimize? Will there be any extra optimization function that will tell me, like a Gaussian or something?
So the question is maybe I'll paraphrase it a bit. So if I have points that are kind of isolated and they don't tell me, they're not part of a trend, how do I pick up a trend that I don't have a lot of points about? And how do I don't get confused by these points that are out of the trend?
Yeah.
Okay.
Yeah.
So one of the things to understand about learning, which is relevant to your question, is that learning says that we're going to be able to do well on data that was chosen from a probability that is similar or the same as the probability we're using for learning. Okay.
Okay.
So if I believe in what I see here, then the probability of this point of this area in this area is very small. See? So if I'm not doing well there, it's not so important.
Okay.
Okay, because my commitment is to do well on the areas that that have high probability.
Local optimization point.
The area that have high probability. Okay, not necessarily. The fact that I have a lot of points here means that there's a high probability that I'm going to get here.
Okay.
The fact that I have only one point here says that there's a low probability that I get here.
Oh, okay.
So in the future, I'm not going to get a lot of points here. So if I make a mistake here, it's not going to be a big mistake because most of the time I'm going to be right. If most of the points are going to be here, and I'm going to have a model that is good here, then I'm good because most of the time I'll be okay. It's only if my data is different than the data in reality. So actually, there's a very high probability that I get here. Then my model will probably be silly because I didn't see a lot of points here. You see.
Right.
So
I think I will add another approach to it is simply to increase the dimension of my learning model.
But then you run the chance of overfitting.
Oh, that's right. So it will increase the chance of overfitting, which you need to take carefully. There are ways to avoid overfitting, like creating the right way of train and test. But if you apply these rules, you can fine tune it until you find the optimal dimension without overfitting.
Optimal complexity of the model.
Exactly.
Now this is something.
It's more of an empirical method.
It's not only it's empirical, but it's very well established in theory actually. So for instance, maybe I think we talked about it in the past, but you can connect. You can connect. There's different aspects of complexity of models, and you can connect that to how much data you need in order to be able to learn. That's in a practical way. That also comes from pack learning, but in a practical way you can do that. So you can, you can think about how much data you need and what kind of complexity of the model you can have. If you have, like, I'll give you a very extreme examples that is really interesting, I think. And Guy, you tell me what the answer is. If now I have 100 points, okay, and the 100 points have 100 features which I can choose from, okay, and how many features will you choose to learn?
I have 100 points and 100 features, right?
Yes. So how many features will you use in the learning?
Exactly. So
my rule of thumb is about 1 to 10. In this case, I'll use my 10 most important features.
Yeah. Okay. Right. So it's about that's what you can do. So you can use a model about 10 features, right?
Right. Most important features.
Of magnitude list. Now you come and you have you want to apply a neural network that is
that will choose the features.
1000 levels deep. What do you think about it?
Okay.
Guy, what do you think?
I think it's kind of bad because when you say 100 layers deep, there is a hidden assumption that you're going to use a lot of parameters that you need to fit, a lot of degrees of freedom.
At least 100, right?
Yes, that's probably much more, but at least 100.
Yeah.
And you only have 100 samples, which means 100 labels.
Yeah.
So you can obviously train the neural network, but I doubt it will have any meaning outside the training set.
Yeah, so it will not generalize. Okay.
it will be overfitting kind of situation. Which
Yeah.
will,
Yes, definitely.
Yes. So
Because given so much
part of
degrees of
the,
freedom, it's easy to encompass the entire training data, but it's just the training data.
yeah, not fit for the future generation. They will
Yes.
which is the main objective of learning.
to benefit the future generation. The
Yes.
future, yeah, exactly.
Okay, good. So
Yeah.
Any other comments or questions for now?
It was really a nice learning. Thank
Good,
you
very
for
good.
that.
Thank you.
Okay, good. So we'll speak next time.
Guy, can you send us the notebook?
Yes,
Yes,
of course.
of
I will
course.
send you. I will send it. And I didn't tell you. I'm going to send the link to the book draft, and I'll say what the number of the exercise is. If you go there, you can click on the exercise and you'll get to the notebook. Okay.
Okay, great.
And you'll get to the notebook and you can run it as well. Okay.
Yeah.
Okay. Thank you very much, and we'll speak later on.
Thank you, everyone.
Thanks. Bye-bye.
Bye-bye.